Hey everyone, and welcome back. Today is just a quick follow-up video on coding PCA, or Principal Components Analysis. I was looking through some of the older videos on the channel and realized that we did a bunch of theoretical videos on PCA, but never went into actually how to code it, and so this is just going to bridge that gap. If I was just doing a coding video, this would be over in a couple of lines, but instead this will be showing you how to code it, but also how do we go from the theory to understanding what the output of this code actually says, and can we actually get the same outputs in a more theory-first kind of coding style? That'll make more sense as we go through the video. Let's generate some fake data for this video. So just 100 data points and 4 columns. The first 2 columns are just normally distributed variables that have nothing to do with each other. The other 2 columns are going to be different linear combinations of the first 2 columns plus some noise. And so we do this because we're interested in whether or not PCA can pick up on this fact about the data and hopefully tell us that we don't actually need 4 variables to represent our data, but less than that. The next thing we'll do is take the mean away from each feature, just so each feature has 0 mean. That'll make our lives a lot easier when we try to do this PCA coding from scratch in just a moment. And now let's just take a quick look at the pair plots of each of our features. So we have 4 features again, and so we'll have 6 possible combinations to look at. x1 and x2 look like they have no real correlation here, which makes sense from the data generating process above. x1 and x3 do seem to have something going on, some kind of correlation. Same thing with x1 and x4. If we look at these next 2, which are x2, x3, and x2, x4, they do seem to have a correlation as well, but it's definitely looser than the ones we see up here. And finally, if we look at x3 and x4, again, a pretty strong evidence of correlation here. So again, just looking at these plots, we have pretty strong evidence, if this is all we saw, that we don't actually need all 4 features to represent the data. We'll probably be able to get away with a lot less than that. And so these observations are just collected here. And now let's go into the built-in way to apply PCA, which is literally just this code cell consisting of 2 lines of code. We go ahead and initialize a PCA object. We say how many components we want. Here we'll just say 4, but in general you can put less than that. And we literally just say PCA.fitX, which takes our matrix of data, which is 100 rows by 4 features, and performs principal component analysis on it. And of course, the first and probably biggest follow-up question is, what are the principal components? So those are stored in this PCA objects.components, and we take the transpose just because we want the columns of this thing to be the eigenvectors, which are the principal components. And so if we print out each of these guys, we see the first principal component looks like this vector, the next one looks like this vector, and so on and so on. So this is not very enlightening, but this is how you would do PCA if you had to just do it in any routine application. But now let's get to the more fun part of the video, which is, what if we had to code up a PCA from scratch instead of relying on a built-in library? Can we get the same results we get here? And let's literally just go through the same steps that we went through in our theoretical PCA videos, which of course are linked in the description below. And the first step of that was calculating the covariance matrix of the data. Now this expression may seem a little bit complicated, but I can actually just walk you through it. The first thing I'll note is that, remember at the top, we subtracted the mean off of each feature, which means that we don't need to subtract the mean in this covariance matrix, but if we had not done that, then we would need to subtract the mean off of each of these xi's. So this just looks a little bit cleaner for us here. So if you go back to the video here, which is linked here, the closed form of the covariance matrix, remember it was just a sum over all of our data points. So in this case from 1 to n, in this case from I in range 100, because we have 100 data points, of xi times xi transpose, where xi is each of your data points, and that's literally what's going on here. Here's your xi, and here's your xi transpose. Those reshapes are just to get them in the shapes we need them to be. We add that, so here's the sum on the outside. And finally, if you go back to that video, you notice there's a 1 over n on the very outside, and that's what this divided by 100 is doing. So this guy is the covariance matrix of our data. And now how do we do PCA? It's simply just taking the eigenvectors, getting the eigenvalues and eigenvectors of the covariance matrix of your data, in other words, using np.linearalgebra.eig and putting the covariance matrix in there, and that's it. Your principal components are stored in there. This ordering part is just to get it sorted so that the eigenvector with the largest eigenvalue comes first. So that's the first principal component, and then we decrease from there. And so we store all those principal components in this variable called principal components by hand. And that looks like this. So the first principal component is this first vector. The next principal component is the next vector, and so on and so on. Now the big question, drum roll please, is that did these principal components by hand which also was not that much code, by the way. This was just a couple lines of code here, but it really shows what's going on under the hood. Are the ones we got here look the same as the ones we got from these couple lines of code up here? And the answer is yes. So if you look at these guys, these are the ones we got by hand. These are the ones from the built-in scikit-learn library, and they look exactly the same. Anyway, this was just a quick video follow-up to the PCA videos, and this code will be on my GitHub, linked in the description below, and I will see you next time.